Our topic for today is PVT behavior of gas mixtures, ideal gas and real gases. This is usually the reporting. In an ideal gas is defined as a gas whose molecules are spaced far apart so that the behavior of a molecule is not influenced by the presence of other molecules, a situation encountered at low densities. The PVT behavior of an ideal gas is expressed by the simple relation P underscore RT, which is called as the ideal gas equation of the state. In a real gas, we also mentioned that real gases approximate this behavior closely when they are at a low pressure or high temperature relative to their critical point values. The PVT behavior of real gases is expressed by more complex equation of state or by PV ZRT, where Z is the compressibility factor. Behavior of gas mixture. When two or more ideal gases are mixed, the behavior of a molecule normally is not influenced by the presence of other similar or dissimilar molecules, and therefore a non-reacting mixture of ideal gases also behaves as an ideal gas. Air, for example, is conveniently treated as an ideal gas in the range where nitrogen and oxygen behave as ideal gases. When a mixture consists of real non-ideal gases, however, the prediction of the PVT behavior of the mixture becomes rather involved. PVT behavior of gas mixture is usually based on two models. Here are the two models of behavior of gas mixtures. First is Dalton's law of additive pressures, and next is Amagat's law of additive volumes. Dalton's law of additive pressure is also called Dalton's law of partial pressures. States that the total pressure exerted by a gaseous mixture is equal to the sum of the partial pressures of each individual component in a gas mixture. This empirical law was observed by Dalton in 1801 and is related to the ideal gas laws. Mathematically, the pressure of a mixture of gases can be defined as the summation. So the sample picture: gas A, volume and temperature, and PA plus the gas B, VT, PB. When it mix, the result is the gas A plus B in VT plus PA plus PB. So in Dalton's law, a mixture of all from gas A and gas B combines all components. Dalton's law's formula: P mix is equals to summation of Pi is equals to P1 plus P2 plus P3 plus plus P key. P sub key represents the partial pressures of the component. Amagat's law of additive volumes. Amagat's law or law of partial volumes of 1880 describes the behavior and properties of mixtures of ideal, as well as some cases of non-ideal gases. Of use in chemistry and thermodynamics, Amagat's law states that the volume Vm of a gas mixture is equal to the sum of volume Vi of the key components gases if the temperature T and the pressure P remain the same. So the Amagat's law of additive volumes: the volume of a gas mixture is equals to the sum of the volume of each gas would occupy if it existed alone, the mixture pressure and temperature. So here's the example. Gas A, pressure and temperature and plus B, the pressure and temperature, and VA and VB is equals to gas mixture A plus B, PT and VA plus VB. In the Amagat's law, oxygen plus into nitrogen 100 kPa, 400 Kelvin, and 1 cubic meter. So it is separate from two gases, from oxygen 100 kPa, 400 Kelvin, and 0.3 cubic meter. In nitrogen 100 kPa, 400 Kelvin, 0.7 cubic meter. Amagat's law of additive volume. Vmix is equals to summation of Vi is equals to V1 plus V2 plus V3 plus V4 plus that plus Vk. Vk represent the number of molecules. Amagat's and Dalton's law. This is the experimental expression of volume as an extensive quantity. It is named after Emily Amagat. Both Amagat's and Dalton's law predict the properties of gas mixtures. Their predictions are the same for ideal gases. However, for real non-ideal gases, the results differ. Dalton's law of partial pressures assumes that the gases in the mixtures are non-interacting with each other, and each gas independently applies its own pressure, the sum of which is the total pressure. Amagat's law assumes that the volumes of each component gas, same temperature and pressure, are additive. The interaction of different gases are the same as the average interactions of the components. Heat capacity. It is seen that the constant is just the dimensionless heat capacity at constant volume. It is equal to half the number of degrees of freedom per particles. For moderate temperature, the constant for a monoatomic gas is Cv over 32, while diatomic gas is Cv over equals to 5 over 2. It is seen that microscopic measurement on heat capacity provide information on the microscopic structure of the molecules. So here's the formula from the constant volume. Cv is equals to 3 over 2 R or equals to 12.5 joules per mole Kelvin. R, R, R over 2 for each of the three translation degree of freedom. R is rational. Constant pressure. Cp is equals to 5 over 2 R is equals to 20.8 joules per mole Kelvin. So constant pressure is equals to constant volume plus R. And that's the end.